Hello, this is Dean Waldo from Pacific Lutheran University doing a quick screencast on irreversible and reversible pressure volume work for ideal gases, essentially the beginning of a treatment that's often covered in the early parts of thermodynamics in the physical chemistry class. So, quick background. Irreversible PV work. So the idea we've got here is that constant temperature, we're going to realize that pressure times volume is equal to nRT, which is a constant. So if we focus on the PV part of that, we're going to start thinking about how we can do work on or by a system through the compression or expansion of a gas. And so the model is that you have a cylinder, and then there's a piston that fits in the cylinder, and that cylinder is frictionless, massless, and the piston itself is rigid, and it's a perfectly fitting piston. And the force that is exerted on that piston is due to the external pressure, PEX. So that's up here. And that force times the area, so the area will cancel the area of the force, area of the pressure. Pressure again is force per unit area, so we're back to force. And if that pressure causes an infinitesimal change in the z position, we'll call it dz, then we're going to think about the work being the pressure external times the area of that piston times the infinitesimal amount of vertical distance it's traveled, and that volume it sweeps out in that dz is going to be the change in the volume of that system. And so we can put those things together. We have the equation dW equals minus PEX dV, and again that sign is basically comes from our definition or the language. So when we're doing expansion, work is done by the system. In other words, the gas that's in here, so we'll just say the gas that's in the piston is pushing that piston, the gas that's in the cylinder is pushing the piston up, and so work is being done by the system. And if that's the case, work is going to be negative because energy is leaving the system, causing the volume change to be positive. And so if the delta V is positive, minus pressure, which has to always be positive, times the change in volume, which is positive, work has to be negative, hence energy is leaving the system. On the other hand, if you're doing compression, work is being done on the system. So the energy of the system has to go up. In other words, work is being done on the system, as I just mentioned. The volume of that gas has to be compressed, and so delta V will be minus. And delta V being minus times the minus sign will give us a positive value. Again, pressure external has to be positive, so the change or the work being done has to be positive. So let's take these concepts and apply that to an example here. This is, well, actually two examples. First, if we're going to do what's called a free expansion, and we set the external pressure equal to 0, we can never do any work simply because we're not pushing against anything in the surroundings. So therefore, free expansion work is always going to be 0 for this isothermal case. And again, let's just emphasize that we're still talking constant temperature. Okay, the second, perhaps much more interesting case is an isothermal expansion from V1, so the initial volume, to a final volume V2. And we can set that equation up. Work is going to equal the integral of pressure external times the change in volume. So if we integrate from V1 to V2, we will then have that integral be a certain value, and the negative of that will be the work done on or by the system depending on the values of V1 and V2. So if we were to take an example in this picture to the left, or the sketch, and we had a gas in the cylinder and the piston's at V1, and if that gas is allowed to push the piston back to a position such that the volume is now V2, you can see the shaded area up here going from V1 to V2 and pushing against an external pressure Px. That area, Px, which is the height of the box, and delta V, which is the width of the box from V1 to V2, that area is going to be equal to, or shall I say, proportional to the work done or by the system. And keep in mind we have to remember the minus sign. So minus P external times the change in volume will be the work done by that system. Okay, so let's put this together and with a new concept. So everything I've described so far is what's called irreversible work, meaning that's the least work we could get out of the system, essentially moving the piston fairly quickly so that the system is never really in equilibrium. Whereas if we move to something what we're going to call reversible expansion compression, we're going to now move the piston so incredibly slow that the gas inside never becomes out of equilibrium. And so we move it infinitely slow, and we're going to ask the question, how much work can we get out of the system if that's the case? To explain or to rationalize this, let's take steps. Let's do the following experiment. Let's look at the left-hand image here. So we're going to look at this system over here. Now imagine you have a piston, and inside the cylinder you've got a gas that is at 10 atmospheres of pressure, and it has a volume of 1 liter, and it's an ideal gas. And then imagine the external pressure on this system is 1 atmosphere, but then we have 9 weights on this piston. Each weight is the equivalent of 1 atmosphere of pressure. So in other words, that piston will be in equilibrium with the pressure inside, so there's 10 atmospheres pushing down, 10 atmospheres pushing up. The piston's not going to go anywhere. So let's do an experiment, so to speak. Let's first take and do an experiment where we remove all 9 weights at once. And if that's the case, our initial pressure is going to be 10 atmospheres and the initial volume will be 1. So we're going to start out here, and I'm going to switch to red, purple. So our initial pressure we're going to push against is 1 atmosphere, and how far is that piston going to go out? It's going to go out until the pressure inside is equal to the pressure outside. So that means PV is going to be constant, so P1V1 is going to equal P2V2. So if we're going from 1 liter and 10 atmospheres to 1 atmosphere, let's make that look more like an atmosphere. There we go. To 1 atmosphere, then we're going to be at 10 liters to keep those two equal. So let's go back to our graph. This piston is going to go all the way out to 10, so if I draw a horizontal line, we're going to go from initial volume of 1 liter to 10 liters, and the area in this rectangle is going to be equal to the work times a minus 1. The minus value of that will be the work done. So let's just calculate what that would be. So the work is going to equal, in this case, minus 1 atmosphere times the difference in volume, which is going to be 10 liters minus 1 liter. So this is V2 minus V1. And so the work in this first example is going to be minus 9 liter atmospheres of work. It turns out that this is equal to about negative 912 joules, just for reference. Okay, so let's go back to this example. So step 1, we just take all 9 weights off at once. The work is easy to calculate, it's just that rectangle. Now let's do a second experiment. In this case, let's remove 5 weights at once. And if that's the case, if we remove 5 weights, how many weights are left? We'll take 1, 2, 3, 4. We'll have 5 weights will be removed. 4 weights will remain on that piston plus the external weight. So we're going to push against 5 atmospheres. So 5 atmospheres. So if we say work, it's going to equal minus 5 liters atmospheres times the initial final volume, which we don't know yet, minus the initial volume, which is 1 liter. So in order to get to the final pressure of 1 atmosphere, we're going to have to do this in 2 steps. So we'll call this step 1. What will be the final volume we get to if our pressure we're pushing against is 5 atmospheres? Again, PV is equal to constant. So therefore 1 times 10 liter atmospheres is going to equal 5 times question mark liter atmospheres. And so that means the volume has to be 2. So we're going to go from 1 liter to 2 liters at 5 atmospheres of external pressure. And that's going to give us, for step 1, a negative 5 liter atmospheres of work. So let's draw that on the figure up here, and I'll just use the blue. So we're going to start out, now we're going to have our initial pressure be 5 atmospheres, and we're going to go over to 2 and back down. So our initial work that we're going to get out of the system pushing against 5 atmospheres is going to be more for that first step. And then after that, the second part, let's call this A, let's say the second part B, we're going to remove the last four weights. Therefore, P external is going to be 1 atmosphere, and we're going to go from V initial, or let's say V1, which will be 2 liters, to V2, or final, which will be 10 liters. So the work involved is going to be minus P external. In this case, we're pushing against 1 atmosphere because we've removed all 9 weights at this point. And our final volume is 10 liters. Our initial volume is 2 liters because we're starting from that different position. So we're going to have minus 8 liter atmospheres. So what is the total work for version 2? It's going to be the minus 5 liter atmospheres plus the minus 8 liter atmospheres, which is going to be minus 13 liter atmospheres, which is about minus 1317 joules. How does this compare with what we saw before? there's substantially more energy we're getting out of the system. There's more work that can be done when we've done this in 2 steps instead of 1. Let's graph that up here again. So in that case, step 2, so this was part A. In this case, part B will be that. You can probably see where we're going, or where we could go with this. For this part C, let's just say, let's remove 1 weight at a time. And what is the work equal to then? We won't do that in this screencast, but I think you can see where that would go. If we did remove all 9 weights at once, the total work we can get out of this would be minus 1954 joules. And essentially that's going to start to look more like something like this. Let's try that again. So I'm just going to draw an approximation if I can get the pen to work. So and then we're getting all this extra energy or work out of the system due to letting it push against a higher external pressure until it reaches equilibrium. So if we were to do this over again, now instead of removing a 1 weight at a time, we're going to remove an infinitesimal amount of weight per time. So in other words, remove so let's just say we remove an infinitesimal weight each time, and so work equals minus integral pressure external dV from V1 to V2. But in this case, we're always changing the external pressure such that it always equals the internal pressure. And we call this a reversible change, or reversible expansion compression. Now, if that's the case, we have minus integral P V1 V2 dV. Now, pressure is defined to be a function of volume. Keep in mind we're still at constant temperature. So work will equal minus integral, and we have an expression for what pressure is equal to. Given the ideal gas law, it will be nRT over V. So we're going to have nRT over V dV V1 V2. And as it turns out, then we know that nRT is a constant. It can go outside the integral, and we're going to have minus nRT integral dV over V V1 to V2, and we can integrate that integral, and that will be equal to minus nRT natural log of V evaluated at V1 and V2, which then will just be minus nRT natural log of V2 over V1. And in our case, we know that nRT is equal to PV, which will mean work is equal to minus 1 liter times 10 atmospheres times the temperature, and the temperature I didn't tell you what it is, but oh, not temperature, silly me, because we already took care of that as the nRT, times the natural log of V2 over V1, which is going to be 10 liters divided by 1 liter. And the work we get when we do this calculation is minus 2,333 joules. This is the maximum work you can get out of an expansion of a gas in a cylinder like this. So work is the maximum. And note the minus 2333 is still substantially larger than the minus 1954. So this is this limiting case we call reversible expansion or compression. We could be the maximum work we can do on the system or the maximum work we can get out of a system. We're going to see how this plays into the first law of thermodynamics shortly. Thank you, folks. That is the main thing I wanted to convey in terms of reversible and irreversible work. Thank you.